Alright, welcome back to another video by Firestarter Graphics and Engineering. Today we're going to continue with our engineering reliability statistics using the Weibull or Ernst distribution. So I'm just going to describe a little bit more of the theory in this video. This is going to be a short video. And then in the next video I'll do theory and an example at the same time. That video might be a lot longer than the others, but it'll be worth it. So if we are given some failure times, let's say some light bulbs, they fell at 100, 200, 300, 400, 500, and 600 hours. So you want to put your data in order from smallest to largest. Now the next step would be, okay, what is the failure rate of a light bulb? What's the probability of a failure at 100 hours, at 200 hours, 300, 400, 500, and so on? So that's why it's important to keep them in this order. So in order to do that, we have to do something called ranking. And there's two different theories. There's Bernard's theory, and then I don't know the other dude's name, but they're both called median ranked theories. So let's kind of go over those real quick. So your failure probability, F, is equal to I minus 0.5 over N, where N is the total number of samples. For example, we have 6 light bulb samples. I is the ranked value, not the failure time like 200 hours. No, 200 hours is a rank 2 in the data. So this one is widely used because it's pretty unbiased for small sample sizes. And for large data sets, it works great. But Bernard's is a little bit more accurate for smaller data sets. So let's say you only have, I don't know, 20 samples of something because that's all you could get, or even 10. And yours is like, crap, that's not a lot. Probably want to use Bernard's approximation formula. So, what do these actually do? Good question. Let's put them in a table real quick. So we have the rank, 100 hours, 200, 300, 400, 500, 6 hours, but those would be time to failures over here. But they're ranked 1, 2, 3, 4, 5, and 6. So now we do I minus 5, I minus 3, N plus 4, and throw it in here. Now what do these numbers mean? Well, this means that at 100 hours, your probability of failure is 8.3%. And at 600 hours, you're at 91.7%. But if we go to Bernard's theorem, he says it's 89.1% failure. So it's a little bit more precise. We have more failure at the lower end, but less at the top end. So, but I've also been told that anything above 50 data points or even 100 data points, things even out and you can't really tell a difference between the two. So if you're working with really small sample size, use Bernard's. But if you have a large sample size, either one will do just fine. So it's all depending on what you want to do. Now, this is the basis of how we're going to start doing some things, because this will tell me, for example, like, okay, well, I know about 400 hours, I'm going to roughly have 57%, 58% failure. But at 500 hours, I'm going to have 73.4% failure. What if I want to know exactly where 63.2 is? You can use linear interpolation, and we know it's between 400 and 500 hours. So my guess is it's probably about 430 hours. So you can use a calculator or do it by hand and use linear interpolation to find, let these be your y values, let these be your x values, and then you can figure out your x value in between along with the y value. We know our x value that we want to do is 63.2, so that'll solve for the y. Anyways, why is that important? Because think of maintenance schedules. If you're running, I don't know, a wind turbine farm That's kind of a ginormous example, but let's say, that's what you have, or you need to replace certain electronic components in something. You want to know when that 63% mark is so that you could say, man, okay, 63 at time 425 hours, 63% of the light bulbs in the building are going to be out. So you want to start changing them at a certain time frame based off of that data. So this is kind of the basics and beginning of where we're going to be moving to next. So anyways, thank you for watching. I know that was boring, but keep with me here.